David Behar, thanks for joining us.
Good to be here.
So there's a widening gap between the median projections and high-end projections. What does new science say about the potential for catastrophic melting?
We're getting a lot of different messages about the high-end potential. Some new modeling, relatively new modeling, is showing that we could have catastrophic melting of land ice, primarily is what we're worried most about, Greenland and Antarctica. And if that were to happen by the end of the century, we could have some very high sea level rise numbers. Combining with the thermal expansion of the ocean, loss of land ice off of Greenland and Antarctica are really going to drive the high-end numbers. At the same time, that modeling in many cases remains experimental. We don't know the degree to which it can project over this kind of time scale, the kinds of phenomena that we saw play out over thousands or even millions of years in the distant past. And so there's still a need to enhance this science, to replicate these results, to do more modeling, get more sophisticated modeling before we can move from kind of an experimental, new science, cutting edge work perspective to what we call actionable science or actionable information. It's the kind of thing that decision makers would move on with actually adaptation planning. The median numbers, the numbers that most models are kind of on either side of, in terms of sea level rise by the end of this century, are not changing significantly over the last 5 or 6 years. We're really seeing still about a meter of sea level rise as the projections by the end of the century in most models in terms of median. It doesn't mean we can ignore long-term catastrophic potential. We can't, and we shouldn't. But whether that becomes actionable information and information that we start to spend money on in terms of adaptation remains an open question.
When does science go from experimental to actionable?
It's a really important question, and one that I think we don't have the answer to, and I don't think we've spent enough time trying to answer that question. A lot of times the worst case scenarios emerge from my community first in the headlines of newspapers. Someone publishes a journal article in the peer-reviewed press, and that's picked up by the consumer media and then picked up by decision makers in my community. That doesn't necessarily mean yet that it's actionable information. Generally, new science needs to be replicated and duplicated by a number of different experimenters or scientists or modelers in order for it to really become mainstream and become actionable information. We don't have a standard yet for that within the sea level rise science community or the climate science community in general. And from an actionable information perspective, we need to put some time into that and answer that exact question.
The 2050 numbers are already locked in. 2050 is a more relevant date for most policyholders in office today than 2100, which is where scientists often go. The 2150 numbers are locked in, yet there's still a lot of uncertainty about them. How is that?
There's a lot of uncertainty as to the sensitivity of the climate system to greenhouse gas emissions and warming of air temperature that results from GHGs in the atmosphere. So what is the response going to be in Antarctica and in Greenland to warming of air temperatures of 2 degrees, 3 degrees, up to 5 or 6 degrees centigrade? We don't know that answer with great precision right now. And so while the amount of greenhouse gas emissions we have between now and the end of the century is extremely important for determining what the level of warming is going to be, the amount of warming that causes an amount of land ice melt and therefore an amount of sea level rise is still poorly understood. And in 2050, which is sort of locked in terms of where we're going, in terms of the impact of GHGs on the environment, there's still a wide range in understanding that sensitivity. So we have forecasts of about 8 to 24 inches of sea level rise, more or less, for 2050. That has nothing to do with greenhouse gas emissions between now and then. It has everything to do with the sensitivity of the climate system and land ice in particular, but also thermal expansion and other factors as a result of that warming. So we need to do a better job, I think, of understanding the sensitivity of the climate system to warming to help us to think about, are we responding to 8 inches in 2050, 24 inches in 2050, and beyond. Beyond is important not just for elected officials, of course. It's important for those of us who are investing in infrastructure. The life cycle of infrastructure is a big part of what we use to understand the life cycle of our response to sea level rise in this case. And a lot of the infrastructure that we're building today is going to be around for 100 years. So even as we invest today and try to think about in the near coming decades, we also have to think about the investment that we're making in terms of the long-term impact of climate change on those investments.
Cities around the country have passed bonds to plan for that uncertain future. $200 million in Miami, San Francisco, about $500 million as a down payment on a seawall retrofit. How are officials today incorporating the science and making decisions about spending big bucks for this uncertain future you're talking about?
In the case of Miami, they're already seeing results of sea level rise. They have clear day flooding that results from higher tides without any rain, without any storm surge going on. And so they're investing for today's issues that they're seeing, and they can think about what's going to happen the next 10 or 20 years and make those hundreds of millions of dollars in investments wisely. For San Francisco, we're investing a down payment, as you said, on our seawall program. That's to look at how to shore up a seawall that has seismic vulnerability, but also think about what we might do related to sea level rise in terms of the seawall. And so we're not yet in the position for us of saying we're going to be at 5 feet or 4 feet or 6 feet or even 10 feet of sea level rise in the construction of the seawall. What's happening with the uncertain forecasts and projections that are coming out is not that we're suggesting we need absolute certainty. We know that that's not in the cards. But rather we'd like to see a narrowing of uncertainty as much as possible. Then our job is to plan for the short or medium term with investments that make sense for those phenomena that we know or are fairly confident are coming, while also building resilience for our adaptation measures for future sea level rise that might be much higher, or it might be higher. We need an adaptive management approach. It's a common strategy in ecosystem science is you adjust your management of the ecosystem, you see how those adjustments work in affecting the ecosystem, and then you make further adjustments in the future. We need an adaptive management approach that addresses sea level rise and other climate phenomena because uncertainty is an irreducible part of future planning. And the techniques and mechanisms for planning under deep uncertainty are getting a lot of attention in the adaptation community now, rightly so, because we're, as I said, not going to be able to reduce that uncertainty, but are going to have to plan in the face of it.
Sounds like a tough time, exciting time to be working on the important bridge between science and policy making. David Behar, thanks for your insights.
Thank you.